I want to use a double integral in polar coordinates to calculate the area of a region. First of all, let me point out that that we can do this because if we think of the double integral of the function 1 dA over some region D, I mean, we're thinking of, you know, we're thinking of this, we have been thinking of this as volume. We've got this region down here in the xy plane, and you've got this height function. Well, if the height function is just 1, essentially you're just making a little cylinder out of that area, the height 1, calculate the volume, it's the area of the base times the height. Well, if the height is just 1, then the area of the base and the volume are going to be the same numerically. The units are different. One is cubic inches and one is inches, square inches or something, but still the number is the same. So I can think of calculating areas by doing a double integral of the function 1. Now in polar coordinates, the dA, of course, is r dr d theta. So there's this r that shows up in there. Okay, so to calculate the area inside of this, okay, so here's what I want to do. Here's my area. It's going to be inside of this cardioid and outside of that cardioid. So let me take a look. In order to draw this, I got to do a couple of different things here. I look at the r theta plane first of all, because 1 plus cos theta is just a cosine curve shifted up 1. So I know what that looks like. This is r equals 1 plus cos theta. And likewise, I know what the other one looks like. It's a upside down cosine curve shifted up 1, so that looks kind of like this. 1 minus the cosine theta. And I use those then to help me see what the polar graph looks like. Essentially, this is my table of points that I'm plotting. So now I'm in the xy plane, and I can see that the blue curve here starts off out at 2. By the time I get to pi over 2, the cycle here is 2 pi. So this is pi. Anyway, at pi over 2, by the time I'm looking in the direction of pi over 2, it's down to, it's down to 1. What am I doing? So it comes out like this. And then by the time it gets to pi, you're down to 0. Then it comes back up to 1 and works its way back up to 2. So that's the cardioid. R equals 1 plus cos theta. 1 minus cos theta does the other thing. It starts here and then it works out and then it comes back into 0. Okay. So to say that I want inside of this one but outside of that one, it looks to me like I want all of this stuff over here, right? Which, by some symmetry, it looks like the top half and the bottom half look the same. So what I'm going to do is I'm going to just integrate from here out to, I guess, there. Looks like what I need is the integral. Looks like I need the integral from 0, that would be here, out to there, which is pi over 2. I was going to double my answer when I was done here because I'm just doing top half of it. Now I got to figure out for r, so for each value of theta in between 0 and pi over 2, so I sort of draw a random one in there, I need to say what's the smallest value of r I'm interested in, what's the biggest value of r I'm interested in. So for each value of theta, and I'm looking at all of these going this way, it seems like each time you start on this curve, which is the 1 minus the cosine of theta, and you stop when you get to that outside curve of 1 plus the cosine of theta. Okay. Then I'm integrating dA, but dA here is r dr d theta. Okay. So there we go. That's the integral I need to do to calculate this area. So I've got 2 times the integral from 0 to pi over 2. R integrates to r squared over 2. Evaluate between 1 minus cosine theta to 1 plus the cosine theta, and integrate with respect to theta when you're done with that. So, actually, let's take the half out in front and cancel it with that 2. So we've got the integral from 0 to pi over 2. I've got 1 plus the cosine theta squared minus 1 minus the cosine theta squared d theta. And at this stage, I can either multiply that out and gather some like terms. It's actually let's do it. What the heck, we're here. I was going to say, or I could just type it into my calculator. It's a definite integral at this point, just one variable. But it's probably not too hard to do at this point, because I think if I square things out, it's going to look a lot nicer. I've got 1 plus 2 cos theta plus cos squared theta, and then the minus sign is going to make this a minus 1 plus 2 cos theta minus cos squared theta d theta, and you got just a bunch of stuff that cancels out. This and that cancel out, this and this cancel out, and we're just looking at now the integral from 0 to pi over 2 of 2 cosine, actually 4 cosine theta. D theta. Okay, I think I can integrate cosine. Is that the sine? Yes, it is, from 0 to pi over 2. And so we've got 4 times the sine of pi over 2 minus 4 times the sine of 0 for a grand total of 4. 4? Just 4? Apparently, it's just 4. That the area inside of this cardioid and outside of that one is 4. I want to do a little reality check here. So I'm looking at this area here. This goes out as far as 2. Huh. Well, because I'm thinking, if it's 2 across and up and down 1, so it would be 2 by 2, that would be area 4. So apparently that this is being, yeah, well, whatever. It's feasible to me that could be 4. Yeah. Anyway, interesting calculation using a polar double integral to calculate area.